So, in this lecture we will look at the problem of approximately counting some combinatorial objects. So, let us look at the particular problem that we are looking at. Our input is a bipartite graph. So, G, this is a bipartite graph, the parts are V and U and E is the set of edges, and the output will be the number of perfect matchings in G. For example, if we had this particular graph, bipartite graph, this is a complete bipartite graph, we can show that there will be 6 perfect matchings. Okay. So, we need to get this number 6. So, we will introduce some notations. So, when we write capital M k, this will denote the set of matchings in G of size k, and small m k we will denote the number of matchings of size k. What we are interested in is computing small m n. So, the exact count of number of perfect matchings is difficult, it is a very hard problem. So, we will look at the problem of approximating this value m n. So, what does approximation mean here? So, given an epsilon, which is a, let us say, real number between 0 and 1, we have to compute a number x, an integer x, such that x is the estimate of the number of perfect matchings. So, this should lie between 1 plus epsilon times m n and 1 minus epsilon times m n. It can deviate from m n, but not by much. Okay. And we need an algorithm which, when given an epsilon and the input graph, computes an x which satisfies this requirement. Further, the algorithm should run in polynomial time. In poly n, so the input graph has some number of vertices that is denoted by the parameter n. So, the algorithm should run in poly n and it should be polynomial in 1 by epsilon. It is a slightly relaxed requirement, in the sense epsilon, if you think of as a number, the number of bits required to represent it may be only log 1 over epsilon, but we are allowing the polynomial to be little larger than that. Okay. So, basically, given any epsilon, we should be able to produce an approximation to m n, such that value that we produce lies between 1 minus epsilon times m n and 1 plus epsilon times m n. That will be what we will call as an approximation algorithm for perfect matching. Now, how do we compute approximate answers to these kind of problems? So, we will use the following fact. Okay. So, this is the key thing that we will use in most approximation algorithms. So, sampling can give approximations. What does this mean? So, let us say that there is a rectangle of length 2 and breadth 1, and inside this there is some particular set. So, the rectangle we will call as R and the set we will call as S. The problem at hand is estimate S. Now, how is this related to approximation algorithms? Well, this rectangle is some set whose size we already know, and we want to estimate the size of a subset of that rectangle. Okay. We will spend a little more time on it later when how this exactly translates into an approximation algorithm for perfect matching, but let us just look at this problem in isolation. We have a rectangle R and inside that is a small area S, and we need to estimate the area of this particular region. So, one algorithm would be sample from R uniformly at random. This would mean, let us say x you take uniformly at random from 0 to, and y also you pick uniformly at random from 0 1, and your point is basically x comma y. Okay. So, that is how you get one sample, and check whether that point lies inside or outside the region S. Okay. Count the number. So, we will do the sampling, let us say n times. Count the number of samples inside S. So, let the count be C, okay, and we will declare C divided by n times area of the rectangle, that is 2 here, as the area of S. Okay. So, this is an estimate. We need to wonder whether this estimate is a reasonable estimate, that is one thing, and the second thing is we should be able to sample uniformly from, let us say, this rectangle, which we can do if we have an access to a uniform random variable, and we also need to check whether a given point lies inside this region or does not lie inside region. Now, this region may be presented in a wide variety of ways, and we need to basically check quickly in polynomial time whether the sample point lies inside the region that we had chosen. So, if we are able to do that, then this entire estimation works in polynomial time. Now, the important question is how good is the estimate. Okay. So, clearly our intuition will tell us that larger the n is, the better will be the estimate, but how large an n can we afford? Suppose the area S was very small, suppose this was S, then we know that we might have to sample more times than what is required here. So, if this is 10 times smaller than this, or let us say 20 times smaller than this, will it suffice if we just sample 20 times more, or do we have to do, let us say, 2 power 20. So, what is the dependency between the size of the area that we are estimating and the quality of our approximation? So, this algorithm is, we will call it as the Monte Carlo algorithm. Okay. Now, the estimator theorem will tell us why this estimate, why this algorithm can work when the size of S is comparable to the overall size. Okay, so what does this estimator theorem says? So this says that n, if you choose n to be greater than 3 by epsilon square times rho, that is a quantity that we have not discussed yet, times log 1 over delta. Okay. So epsilon we already know what it is, we do not know what delta is, we do not know what rho is, but the estimator theorem says that if it is greater than this quantity, then the estimate is reasonably good. So let us look at what is rho and delta. So let us look at some particular set U whose size is known. So we will call this as the universe, which is rectangle for us in the earlier case, and the universe is of known size. Okay. And there is a set G whose size we need to estimate. Okay. If we are given one particular sample point from the universe, we can tell whether it belongs to G or not in polynomial time, but the total number of elements in G we do not know. The universe may be a large set, its size is known. If we thought of the algorithm of generating all elements of the universe and checking whether it belongs to G or not, that is an exponential time algorithm usually, because the size of the set U could be very large. Okay. And we will call this ratio of these sizes as rho. Okay. So this in some sense captures our intuition, because if rho was really small, then the dependency on n is inversely proportional. So as rho becomes smaller and smaller, the number of iterations that you will have to run could become very large. When we are looking at algorithms, we can afford to have rho small, but not, let us say, exponentially small. 1 by, let us say, n raised to k is okay, because then the number of times we will have to run our algorithm is something like a polynomial will be 1 by a polynomial will be okay for us. Okay. Now we need to understand what is delta. Okay. So this algorithm, this can give various answers at various times. It depends on how, what all we sampled. Okay. This was our this was our correctness criterion, that is the answer returned should lie between 1 minus epsilon and 1 plus epsilon of the correct answer. Okay. So we can look at probability that the, let us call x as the estimate, it lies between 1 minus epsilon times the true value, let us call that as let us say mn, and 1 plus epsilon times mn, or whatever was the value that we were estimating. Minus epsilon times, let us say, if the alpha was the true value. Okay. So we could look at what is the probability that the estimate lies between 1 minus epsilon of the true value and between 1 minus epsilon times true value and 1 plus epsilon times true value. We could compute this probability, or we could say that we want an algorithm wherein this probability is, let us say, significantly high. This should be greater than 1 minus delta. In other words, we want our algorithm's correctness criterion are as follows. One, x should lie between 1 minus epsilon times alpha and 1 plus epsilon times alpha with probability. X should lie between these, but that will happen with a certain probability. So this probability should be greater than 1 minus delta. In other words, probability that the complementary event happens, that is x minus alpha, the absolute value of that being greater than epsilon times alpha is less than delta. Okay. So, if you think of this as the error, okay, then we are saying that the probability of error is at most delta. So, if we have this condition, how large an n should we choose so that this algorithm, the Monte Carlo algorithm, works properly? Okay. And the estimator theorem states the following. Monte Carlo algorithm works properly. So, works properly means it satisfies the correctness condition if n is greater than 3 by epsilon square rho times log 1 by delta. Okay. We will quickly see the proof of this. The proof is just an application of Chernoff bound. Okay. So, what does Chernoff bound say? If you look at IID samples of a random variable, let us say x1 or x2, xn are IID samples, and each xi is a random variable whose mean is some fixed number, the probability that the sum of them x minus mu, mu is the expectation of the sum, this being greater than, let us say, delta times mu, happens with probability which is less than 2 times e raised to minus delta square by 3 times mu. Okay. So, basically Chernoff bound says the sum of Poisson trials, what is the probability that it is greater than delta times its expectation, that is extremely small. So, we will just apply that to prove the estimator theorem. So, let us set up our random variables properly. So, our random variables are as follows: yi equals 1 if the ith sample belongs to G, and this is equal to 0 otherwise, and y is equal to summation yi, which can be viewed as number of samples in G. We use y to estimate G. So, the estimate for G, we will call it as G tilde, that is equal to y by n times size of u. We want to compute the probability that the estimate lies between 1 minus epsilon times size of G and 1 plus epsilon times size of G. Okay. Let us call this as event E. So, this probability we want it to be high. We could look at the complementary event E complement, that is probability that, so probability of E complement or the error probability So, this is same as probability that G complement minus size of G is greater than epsilon times size of G, and the absolute value is greater than epsilon times size of G. Now, how do we compute this probability? Okay. So, this we can simply write it as probability that the estimate for G is summation y I by n times u, and the value of mod G is equal to rho times size of U. So, this should be greater than or equal to epsilon times mod G. This is the event whose probability we need to estimate. So, we can write this as probability that summation yi minus rho n, its absolute value is greater than n divided by mod U times epsilon times size G. Okay, we have just rearranged terms. So, this is the probability that sum of random variables 0 1 random variables is greater than, I mean minus rho n, its absolute value is greater than, we can write it as y minus rho n. What is rho n? Rho n is actually expectation of y, because each yi its expectation is rho, and therefore, when you have n such sample, that is just expectation of y. So, y minus expectation of y greater than epsilon times n into G by U is again rho. So, this is again expectation of y. So, this is probability that y minus expectation of y is greater than epsilon times expectation of y. Here, since y is sum of random variables which take 0 1 value, we can say we can apply Chernoff bound, and so therefore, this probability is less than 2 times e raised to minus epsilon square by 3 times mu, the mu being the mean of y, which is n times rho. Okay. So, our error probability is definitely less than 2 times epsilon square by 3 times n rho. So, error probability, if you think of it as delta, and if we equate to this quantity, okay, we will get delta is equal to 2 times e raised to minus epsilon square by 3 times n rho. Okay. In other words, if we choose our n accordingly, I mean whatever be the n, this is the maximum amount of error that we can have. Now, if this is the amount of error we can have, how large should n be? Okay. So, an n which satisfies this equation will be sufficient. So, we can write it as e raised to minus epsilon square by 3 n rho is equal to 2 by delta. Taking logs on both sides, we will get epsilon square by 3 times n rho is equal to log 2 by delta, or we can say n is equal to 3 by epsilon square by rho into log n by delta, which is what our estimator theorem stated. So, as long as error is reasonable, if it is let us say 1 by poly, and the fraction of good cases or the size of G is bounded by a polynomial in the size of the total universe, this algorithm you can choose n to be polynomially bounded. Okay. So, the estimator theorem works properly when rho is reasonably small. If it is extremely small, we cannot use the Monte Carlo algorithm. So, when it is very small, let us say if the size of S is 1 by 2 raised to n of the entire size, then we will have to run it 2 raised to n times to get a reasonable success probability. So, we need to show that whenever we are running Monte Carlo algorithm, the set is of reasonable size, that is the first requirement. Okay. So, now how do we use this notion of Monte Carlo algorithm to generate or to count the number of perfect matchings? Maybe there is a universe which contains elements which are perfect matchings and let us say which are not so perfect matchings or other objects. If we could, and the universe's size we could somehow estimate, and then we could sample from that and generate, but this is not a, I mean we do not have any algorithm of that kind. So instead what we will use is an idea which can be used in a wide variety of cases. It is called self reducibility. Okay. So self reducibility is a key property that is required for running the kind of Monte Carlo algorithms we will be thinking. Okay. So what does self reducibility bring in? So whenever, so we have been defined what is self reducibility, but whenever there is self reducibility, the following statement is true: approximate counting is equivalent to uniform sampling. Okay. So once again, whenever a problem is self reducible, we haven't defined what is self reducible. Approximate counting, which we had earlier done via Monte Carlo algorithm, can now be done via uniform sampling. Okay. In Monte Carlo algorithm, you require the good cases to be part of a large universe, and the good cases is a significant fraction of the universe that we are considering. Now uniform sampling essentially means we will generate only instances which are good instances, okay, but we can do that uniformly. So the earlier picture was we had this universe U, and from that we were sampling elements G. We were sampling U uniformly at random. Now if we could sample G uniformly at random, even when we do not know the size of G, this uniform sampling can be used to do approximate counting. In order to do this, a key feature required is what is known as self reducibility. Okay, it is a natural notion. So let us understand it via, let us say, perfect matchings itself. So imagine that we had access to an oracle or a program which generates perfect matchings uniformly at random. Okay. So there were, let us say, 125 perfect matchings for a particular graph. Each of those is being generated with 1 over 125 probability. Okay. Now how can we use that to count the size? Okay, the idea is the following. Let us look at all the possible matchings, and let us look at one particular matching edge E. Okay. Now the matchings could either contain E or not contain E. So if you look at the number of matchings of size k, this is equal to MKE plus MKNE. The number of matchings of size k essentially is a sum of matchings which contains the edge E and which does not contain the edge E. If we could uniformly sample, we could estimate the ratio. So this is the key claim. If we could uniformly sample from capital MK, we can estimate MKNE divided by MKE using our Monte Carlo algorithm. Okay, when we say using Monte Carlo algorithm, we can assume that these, I mean, whatever we are approximating from whichever space we were sampling. Okay. So we could sample from MK, and let us say we sample for let us say 1000 times, and we look at the number of elements which have the edge E and the number of edges which does not have the edge E. Their ratio is essentially a good estimate of MKNE by MKE. Okay. But if so, this ratio could be estimated, but what is the advantage? If we estimate this ratio, can we really compute mk? Okay. So, mkne by mke, this is a ratio that we have estimated. Now, suppose we knew mkne, we could clearly compute mke as well. Okay. So, if we knew mkne and r, then mke can be computed, just a multiplication, right. Mke is mkne into 1 by r. So, this can be computed, and once this is computed, we can compute the sum, which is mk. So, if we could compute this ratio and mkne, we are done in a certain sense. We have to argue that the errors in the approximation do not add up to render our algorithm futile. Okay. That we will do later. So, mkne is what we need to estimate, but that is just another instance of approximate counting. It is a smaller instance. Okay. mkne is the number of perfect matchings without the edge e. So, that is a smaller graph. You need to count the number of perfect matchings in a smaller graph. We could again use the same idea to estimate that. Okay. So, we needed to estimate the number of perfect matchings in some particular, or the matchings of size k in a certain graph. Now, we need to find the matchings in a smaller graph, matchings of size k in a smaller graph. Okay. So, for that again we can use the same idea. So, this is called self reducibility. So, when we could do self reducibility, so this is an intuitive proof of why self reducibility would mean approximate counting, because if we could self reduce, that means reduce the problem to a smaller instance. Okay. So, we wanted to count mk. Now, I mean on some particular, let us say graph G, now we have again mk on a smaller graph, this graph minus the edge e. If we could count that along with this estimate, the estimate we obtain via uniform sampling. So, that estimate and mkne together yields the count mk. Okay. So, we had to count the number of perfect matchings. We said we will approximately count it. In order to approximately count, we needed to sample from a universe which contains, let us say, the perfect matchings and other elements. But instead of doing that sampling, we now say that if we could just generate uniformly at random all the perfect matchings, then that is good enough, because of the self reducibility of this particular problem that we are addressing. So, there are lots of other problems which are self reducible. In all those problems, we can use this method, that is, I mean, if we could uniformly sample, then we could approximately count. The other direction is also true. If you could approximately count, then you can, in some instances, you can do a near uniform sampling. So, we need to sample uniformly, but sampling uniformly is difficult. So, what we will do is we will do near uniform sampling. Okay. And we will have to show that uniform sample, when we looked at our Monte Carlo algorithm, it required uniform sampling, but one can analyze this problem as well, that is, if we could sample nearly uniformly, it is not exactly uniform, but very close to uniform, even in those cases we can compute the approximate values fairly accurately. Okay. So, what is near uniform sample? So, let us say you are looking at a universe U, and let us say the sampled element we denoted by, let us say, U itself. If you look at the probability that the sampled element is equal to, let us say, a fixed element omega. Okay. This probability we would expect it to be, let us say, I mean 1 by n, where n is the size of the universe. Okay. So, in uniform sample what we expect is for every omega, where omega is an element of the universe that we are sampling. So, probability that the sampled element is omega is equal to 1 by n in case of uniform sample. Okay. When we say that something is near, so this is uniform. Near uniform means we are allowed to deviate from 1 by n. So, this minus 1 by n, its absolute value divided by 1 over n should be less than, let us say, rho. So, we will call that as near uniform sampling with parameter rho. Okay. If rho is 0, that means we have uniform sampling. So, what we will show later on is that near uniform sampling will also suffice. Okay. So, now approximately count the number of perfect matchings. All that we require is we need to do a near uniform sampling of the perfect matchings in the bipartite graph. Instead of sampling the perfect matchings, so what we will do is we will sample Mn union Mn minus 1. So, Mn was a set from which we needed to sample. Now, here sampling, from now on sampling would mean near uniform sampling. Instead, we will do an almost uniform sampling or a near uniform sampling from Mn union Mn minus 1, and we will see that our algorithm can be slightly modified to compute the values of Mn from these quantities. Okay. So, let us say that we will be doing near uniform sampling, but let us pretend that we are doing uniform sampling of Mn union Mn minus 1. Okay. So, when we are doing the sampling of Mn union Mn minus 1 or later on Mk union Mk minus 1, okay, we can estimate the following quantity, which is, let us call this as Rk. So, Rk is equal to Mk, that is number of perfect matchings of size k by Mk minus 1, because the entire universe from which we are sampling consists of two kinds of matchings, matchings of size k and matchings of size k minus 1. If these matchings formed significant portion of the entire thing, then we know that Monte Carlo algorithm would estimate Mk by Mk minus 1 with good accuracy. Okay. So, what we will do is we will estimate Rk, and we will say that R1 is basically equal to M, or the number of edges. Okay, because anything could have been correct. I mean, when you take R1, that means it is the number of matchings of size 1, that is M. We can readily estimate it. I mean, we do not have to find the ratio, we will just take that as a value. Now, if you compute Rk, the product over k varying from, let us say, n to 1, this is equal to Mn. Okay. So, in order to estimate Mn, we need to estimate just Rk. So, you can write the entire steps, missed out many steps in between, but we will, I mean, we have not given complete proofs, but this is our outline. Estimate Mn by computing the product by I equals 1 to n Ri, where Ri is equal to Mi divided by Mi minus 1, and R1 is equal to M, number of edges. Okay. Now, where all could we go wrong? Well, first of all, each of these Ri's we are just estimating. So, there could be error, could introduce error in each Ri. Okay. Second, each Ri error might be small, product of Ri's could have accumulated, product of Ri could accumulate error. Right. The individual Ri's are not so much error prone, but maybe the product has. Okay. Another issue is, how do we estimate Ri? This requires sampling from Mk union, so Rk, Mk union Mk minus 1 can be uniformly sampled from this. Even if we could do uniform sampling, is it guaranteed that Rk, I mean that Mk and Mk minus 1 are significant portion of the entire collection? Is Mk and Mk minus 1, or we can just simply ask, is Rk reasonably large? That is, if one of the MI's, capital MI's was very small in comparison with the MI plus 1, then when you do the Monte Carlo algorithm, the number of iterations that is required to guarantee the accuracy of Rk could be reasonably small. So, is this reasonably large? These are some important questions. So, we will see that each of these steps could be satisfactorily answered, and therefore, we could estimate Mn to reasonable accuracy by this method.